Good morning, dear student. We were discussing about block diagram reduction techniques in the previous class. We will see now how to reduce the block diagram with multiple inputs and multiple outputs. Okay, so I'll be going directly to the slide in which we have multiple inputs and multiple output handling block diagrams. Okay. Okay, so now in today's class, we will be dealing with how to reduce a block diagram which will be having more than one input. Okay, so multiple input and multiple outputs if we have, how to handle such systems. Okay, so in this example, we have two input. Okay, so we have two input and we have one output. Okay, so you have all heard of already superposition theorem. So if a system is linear, if two inputs are applied, you can contribute the effect of each input separately, and you can add those effects to get the final results or an output. Okay, that's what we will be doing here. So I have input R, I have input U. So for this particular block diagram, what I do is I consider one input at a time and I'll calculate the response. And the two response what I'll get by considering one at a time, I'll be adding them up to get the final response or the final output. Okay. So now what I do is to start with, I'll mask the other input. Okay, so I'll mask the input U. Okay, and I'll get the system something like this. Okay, what I did, I blocked the one input and I'm considering the other input. Okay, so I'm considering the input R and I am blocking the input U. So if I am blocking the input U, what will happen? The summer doesn't have any significance. The other input, if it is not there, the summer you can remove it and you get G1 G2 are in cascade. I can group them. So this is what the reduced block diagram for the condition U is equal to 0. What I did, I blocked the second input, I considered the first input R here, and I have rewritten the block diagram. Okay, so now it is very simple to calculate the output for the input R. Okay, I'm calculating the output for the input R. So what I can get here, this is a unity feedback, unity feedback negative loop control system here. Okay, negative loop control, negative feedback control system. So we know how to simplify this. Okay, how to simplify this loop we know. So what is the CR value we have? That is the output response for the first input only. Okay, we have blocked the other input, we got this value, that is G1 G2 divided by 1 plus G1 G2 into input R. Okay, that is what the output C of R, we will get it. Okay, so what is C of R? I repeat once again, C of R is the output for the input R. Okay, now I'll be considering the second input now and I'll block the first one. So blocking the first one is you are removing the summer itself because R is not there, because R we have made it 0. Okay, so now I have to put -1 there because why? Because I have to put -1. You can see here to this summer there is one signal entering with a negative sign. So unity signal minus sign is there entering to the summer, though the input R is not there. While removing the summer, care has to be taken that the minus is incorporated. So that's what we have done here. -1 block I have taken here and the summer we have removed, and the input, second input we have considered U here. Now I wanted to calculate what is CU, that is output for the input U. Okay, so this is what the block diagram we have by blocking the input R and keeping the input U. Okay, so now you can rewrite this way. We are not comfortable, we are comfortable something like this pattern. I should have an input entering from the left side, I want output coming out from the right side. We are visually comfortable with this pattern. I am just rearranging the block, I'm just dragging the summer to the left and I'm taking this G1 and minus 1 here in the bottom, and I'll be taking G2 in the forward, just rearranging the term so that the conventional canonical form I can visualize. Okay, so what I have done it here, these two blocks I can group it. How I can group it? G1 I have taken, this minus I can take it to the summer here. Okay, summer plus I can make it minus, this minus you can take it here, and this looks like a negative feedback control system, standard negative feedback control system or canonical form. So how to simplify this? We all know that forward path gain divided by 1 opposite sign of this, that is plus forward path gain into feedback path gain. So you will be getting the output CU. How I can write it? G2 divided by 1 plus G1 G2 into U, because I am giving a direct expression for the output for the input U. So I have to take the input here, that is U we have taken. Okay, so what I got now? I got now two outputs, one for the input R and another for the input U. So what I am doing is, I am now, adding both. I am adding both to get the final response or the final output. That's what we have done it. So I have computed CR in the previous slide. We have computed CU. You have to add these two, and this is what the equation you get. So this is what the output for the given block diagram. Okay. Hope you understood this. Very simple. Okay. So next we have one more multiple input system here. You have three inputs here. Okay, you can see here you have three inputs. Same procedure we have to adopt. Okay, so earlier we had two, so we were blocking one, keeping the other. Here what we have to do, we have three, so we have to keep one and we have to block the other two in each trial. So like that thrice you have to do, because three input, I have to take all the three at a time, and I should block the other two, the rest two I have to block it, and I have to calculate the corresponding output C. Okay, so look into the block diagram. I have U1, I have U2, and I have R. These are all the three inputs here, and entering to this block diagram, and I have only one output C. So same procedure here. What I do is, I'll first block the other two inputs, that is U1 and U2. I will block it, and I'll keep only the input R. I'll keep input R and I block U1, and I'll be blocking U2. So if you're blocking U1, this summer will not be there. If you're blocking, this summer will not be there. Correct? So G1 and G2 are in cascade. You have to group them. H1 and H2 found to be in cascade because summer will not be there. U2 is 0. So you have to group them. So this is what the simplified block diagram, it looks like a standard canonical form, and you can simplify this and you get what? Output for input R. So output C for the input R, I call it as C subscript R, that you can compute. Okay, so this simplification, we have already seen how to simplify this. Forward path block gain divided by 1 minus, why I have minus here? Because here the sign is plus. So 1 minus forward block gain into feedback block gain into the input. Okay, that is what the output expression we have. So we have taken it. Okay, next. So that is what the first input contribution is over. Now second input, I'll be considering it as U2. So I'll be considering the second input U1. So if I keep U1, I have to block input R and I have to block the other input U2 to 0. That's what we have done. So you will not find this summer here, and you will not find one U2 corresponding summer will not be there. Only U1 you have. Again, these blocks I will be arranging so that visually we are comfortable to see a canonical form like this. Okay, so I want input entering from the left side, I want the output coming out from the right. So you are rearranging the block, you get G2 as the forward block, and this block are in cascade. You have to group them, so you will get this as a feedback path. Now you can simplify this. So this is a standard canonical form we have, okay, of a positive feedback control system. And how to simplify? Forward block gain divided by 1 minus, since I have plus here, I have to take minus here, minus forward block gain divided by the, forward block gain into the feedback block gain, okay, into the input. Input is U1, I have to take it. So this is what the C1 we have, okay, C1 due to input U1 only. Okay, similarly I'll be repeating for the third input. So I will be blocking the input R and U1 to 0, and I consider only U2. Okay, again I'll be rearranging the block. I'll be getting something like this. Okay, this is what I'll be getting by rearranging the blocks. Okay, you can now simplify. This is standard canonical form with a positive feedback. So you get this expression very similar to the previous case. You can write an expression for C2, you can call it as CU2, you can call it as, because we have this corresponding to U2. Okay, they have named it as C2, we will keep it. So we got this C2 due to U2 alone. So now what we have to do is superposition principle. There are linear system. So superposition system, we are we are adding all the contributions, considered each input separately to get the final output. So final output C is what? The C due to R alone, C due to U1 alone, C due to U2 alone, you have to add, and this is what the final transfer function you get. Okay, add all the three, you will get this particular transfer function. You please calculate and simplify at home. This is what you will be getting the output C. Okay, so next one. Again, here it is a multiple input, multiple output system. So far what we were discussing only multiple input with a single output, correct? Here we have increased the complexity. Here we have two inputs and two outputs. Okay. So here, we have to see what we are calculating. Based on that, we will block the other inputs. Okay. So multiple input, multiple output system, they will give clearly what we have to determine. So we have to determine C1 and C2 due to R1 and R2. Okay. C1 and C2 we have to compute due to R1 and R2. Okay. So what I do is, first I will be calculating C1 alone. So while computing C1 alone, okay, I should not consider C2. So I will block C2. Okay, I will block C2. I will consider only C1. Okay. Next, while calculating C1, I cannot keep R1, R2 both at a time. I'll keep R1 once and calculate what is C1 corresponding to R1. And I'll keep R2 input and I'll compute the C1 corresponding to R2. Okay. And I add those two, output components to get the final C1 output. Okay. So I will do that. Okay. So I have to determine what here C1 and C2 due to R1 and R2 I have to calculate. Okay. Okay, now what I do is I'll ignore the output C2 because both the output I cannot compute at a time. I will ignore C2. I will consider only C1. Okay, and again I'll consider only one input R1 and R2 I will mask. Before I mask R2, I have to write the reduced block diagram keeping C2 0. So if you make C2 0, okay, you can write the reduced block diagram like this. Okay, you can write the reduced block diagram like this. Okay, it may be a little confusing to imagine. You can do that. It's very simple. See here, from this summer I have G2 going, G2, correct? So in other words, C1 through G2 coming to this summer. I have from C1 through G2 I am entering to this summer, correct? So now from this summer, output of this summer through G4, through G3, going to this particular summer, correct? We have done that. Through this summer, from this summer, through G3 and G4, we are reaching this summer. This summer we are reaching, okay? And C2 is now blocked, or C2 made 0. Since C2 is made 0, G4 and G3 found to be in cascade I have grouped, and output of the summer is through G3 and G4 I am reaching this particular summer. So this is what the reduced block diagram I have. Okay, hope you understood that. Okay, so next what I do is I am not able to go to the next slide. Okay, so this is what the rewritten block diagram keeping C2 0, which we have seen in previously. So now what I do is okay. So now I'll make okay. I'll make very sorry. I think I'm going to the previous example. Okay, so now what I'll do is, so previously what I did, I considered, wait, sorry, I'm just missing the slides. Okay, this is what the slide I was looking for. Okay, so what I have done is previously I have blocked the C2, correct? And now I'll be blocking the second input, and I'll be considering only the first input. So consider first input and block the other input. You will be getting a block diagram, something like this. So what I did here, I blocked the R2, and this is what the simplified block diagram. You have to calculate the C1 output, that is first output due to R1. I'll be calling that as C subscript double one. Okay, what this subscript says, I am computing the output 1 due to the input 1 only. Okay, similarly then you have to block the input here, and you have to consider only the R2 input, and this is what the simplified block diagram you will get it. Okay, after manipulating the block diagram, because you are blocking R1, you are blocking C2, you will be getting a reduced block diagram, something like this. So this is the standard canonical form we have, and you have to simplify this output. I call it as C subscript 1 2. What does it mean? I am computing the output, first output for the second input. Okay, this is the first output for the first input, this is the first output for the second input. So this simplification is very easy. This is what the standard canonical form, the formula, and you can write the equation for the output. We have done it. So now final computation of the output C11, which is equal to the the output due to the first input, first output due to the second input. You have to add, and this is what the equation you have. Okay, so this is what the equation you have. Okay, so now we'll be moving to the next point. Okay, so what I do now, I will be ignoring C1 now. I'll be considering only output, second output. Okay, so I'll be considering now the second output C2, and if you block C1, this is how the block diagram look like. Okay, so given block diagram, if you refer, you will be blocking C1 there. Okay, and this is what the new block diagram you will get it. Okay, so C2 we have to calculate for the two inputs R1 and R2, two inputs R1 and R2. So consider R2 keeping R1 0. Okay, you get this particular block diagram. Okay, you have to trace the path, you will get it. It is not that tough. Only thing is path you have to trace. The blocks which are in cascade you are grouping, and you will be rewriting the block diagram. Okay, the cascade block simplification we have done, whichever comes in the way. And for making R1 0, you get C2 2. What does it mean? The second output for the second input. This is what the expression. Similarly, we will make R2 0. You get R1 input entering considered here. And this is what the simplified reduced block diagram for that particular condition. What is the output we are getting now? It is C2 1. That means we are getting the second output due to the first input. Okay, second output due to the first input. Other parameters are blocked. Okay, so this is what the expression we have. Again, according to superposition, second output I can write it as the second output due to the second input, and plus the second output due to the first input alone. Okay, considered one at a time. So this is what the transfer function we have, or sorry, not transfer function. This is what the output equation we have. Okay, so This is how we will be computing multiple input, multiple output system. Okay. So now this we have done it. Okay. This is how we will be calculating C1 and C2. Okay. So next we have the concept writing a block diagram for a armature controlled DC motor. Okay. This is an armature controlled DC motor situation we have. For this we have to write the block diagram. Okay, I'll go to the previous one. Hope you have clear how to write the what we call output equations for the multiple input and multiple output system. Anyway, okay, so this is what the block diagram for the armature controlled DC motor. Okay, armature controlled DC motor. So here let us not waste time in writing the equations, because the same problem we have discussed in module 1 already. All videos are uploaded and it is available. Please refer how to write how to write mathematical equations, differential equation to this particular armature controlled DC motor we have learned in the previous classes. So direct equations I have written here. Okay, so direct equations I have written, that is the voltage VA. Okay, that is the voltage VA. Okay, we will be applying. Okay, and we will be controlling the motor. Okay, we'll be controlling the motor. So this is what the equation we can write here. We have inductance L here, LA here, armature inductance, armature control circuit inductance. This is the resistance. Okay, so this subscript A we have just to say that we are connected to the armature. Okay, similarly from the other side, the other side we have one more equation, that is mechanical system we have. To the other side, to the right we have mechanical system. For that we have one more equation here. Okay, so we have two equations, one for the electrical section and the other one for the mechanical system. Okay, so I'm viewing here armature voltage control, armature what we call loop or armature circuitry separately. In electrical domain we have, and mechanical section we'll be having one more equation here. So these two equations we will be implementing separately, and finally we will be connecting them. Okay, so how to write the equation, how do I get the equation, it is already discussed. You please refer. So these are all the two equations I can write for the given given electromechanical system. Okay, this is an electromechanical system. For this we can write these two equations. Okay, so now for this thing I can okay, so first I will take the first equation. Okay, first I will take the electrical section equation, and I have an equation something like this. So you can see here, output is the armature current. Output is the armature current that I'll be feeding to the armature of the motor, to control the speed or whatever it is, flux or speed. So what I do is I have to get an expression for IA of S. I repeat, for IA of S, I have to get an expression. So for that, what I do, I'll send this term to the right, correct? I will send this term to the right, and I'll take this term in the denominator. Okay, so VA minus S minus KB into W of S, angular displacement, what we have learned. So that I'll be taking to the what we call to the right, and you get an expression for IA of S, correct? Okay, so you can see that VA of S plus, sorry, minus this term, this minus this term, and whole divided by this term is what IA of S, correct? So that's what we are trying to write here. Okay, so VA of S is entering to a summer, and W of S through KB, constant KB, entering to the summer with a negative sign, correct? And this particular difference is multiplied by what? 1 by this term, 1 by LAS plus RA. Okay, 1 divided by LAS plus RA, I have rewritten, okay, because I wanted S to the left here, because I can take inverse Laplace very easily. So I have taken the standard pattern representation. Otherwise, this block is equal to 1 divided by this particular coefficient of this IA of S, okay. So this minus this signal multiplied by this is what IA of S, okay. So now in this equation, VA of S is an input, this is an input, and IA of S is the output. So I have taken IA of S here as an output, and W of S is an input, and VA of S is an input here, and this is what the output, and this is what the piece of block diagram I can write for the equation 1. Any doubt? Hope it is very clear. Get an expression for IAFS. While getting an expression for IAFS, you get that V of S minus KB into W of S, omega actually, KB into omega S will be having to the right side, and whole thing has to be divided by this, and to get IA of S. That's what this block diagram says. Okay. So now what we do is, I'll go to the second equation. You have here second equation, right? Let us implement the second equation. Let us implement the second equation now. Okay. Second equation, we have something like this. Okay. So as in the previous equation, we found IAFS as an output. That IAFS is the input for the mechanical system we have. That armature current is what the input to our mechanical section, and rotation is what the, angular velocity is what the output here we have. Okay. So the rotation is the output, or angular velocity is what the output here. So this is what the block diagram we have. So refer the second equation. Okay. So get an expression for this omega S. Get an expression for omega S from the second equation which we have written. Okay. So this is how you get the block diagram. So remember, IA of S is the input which is passing through the KMA constant. Okay. So you will be having torque now. Torque generated, the current is generating a torque, and this is what the amount of gain we have in the mechanical system. So you have to pass through that. So that's what the amount of angular velocity will be getting as an output. Okay. So this is how we have implemented the second equation. So output is this angular velocity, and input is the armature current. So this is how we can write the block diagram. So now the first and second piece of the block diagram, we have to group it. Okay. You can see here from the first equation, we have this piece of block diagram. From the second equation, we have this particular piece of block diagram. So for the first equation, electrical system. So electrical system, we have a current as an output. It takes, what are the input? It takes the angular velocity from the mechanical system, and it will take the input applied voltage, and it generate a armature current. Correct. So armature current here is generating a torque which leads to the angular velocity. Correct. So I'm clubbing these two equations now. So this is how I'll be getting. Just to join this IAFS and this IAFS, you have to join. This omega S and this omega S, you have to join. So this is what the combined block diagram we get. Okay. So this is the equivalent block diagram representation of armature controlled DC motor, the figure which we have seen in the previous slide. Okay. So this is very important. Okay. So this is how we write the equations to the, block diagram to the given electromechanical system. So it is very easy now to simplify this. You can simplify, you get an expression for voltage and this angular velocity ratio, control ratio equation. You can get forward path gain, you can compute. So this is a standard canonical form. Only thing is you have to multiply these three blocks. So this is a standard canonical form which we have designed for the armature controlled DC motor. Okay. So all these preliminaries which we have discussed in the module one, that is electromechanical system modeling, we have discussed. There we have learned how to write the equation. The same knowledge we have used and extended here to write the corresponding block diagram. So here we have electromechanical system block diagram for the armature controlled DC motor. Okay, so hope you have understood. Okay, with this we will conclude the block diagram reduction techniques and block diagram algebra. So next class we will be taking up the signal flow graph. Again, it is a graphical method which help us in arriving at the transfer function. We will see that in the next class. Okay, thank you.